Yes.
And your family name will appear now.
Okay, Alexopoulos.
So.
Thank you very much, but I will present the research work led by Professor Metaxa. My apologies. Okay, Professor Metaxa, together with an end user, it's Alexandros Admix, Alexandros SA, dealing with two different problems. Ice formation, just like typical for Norway, and of course some addition with nanoparticles similar to the work performed by IFW, Leibniz. Okay. So the story goes like this. Before almost one decade, I was involved in a project with reinforcing resins at the nanoscale. And at the same time, Professor Metaxa also had another project trying to reinforce cement-based materials with the same reinforcement, carbon nanotubes at the moment. Now, this one is a blended problem. How can we involve nanocomposites or nanostructures for de-icing? I don't want to motivate on the problem. People from Norway can answer your questions very much. We don't. We have snow at the northern part of Greece, but of course, as you can imagine, there is a technological problem. Now, what could be the case? What would be the solution of the present study? Is we involve carbon nanostructure in cement-based materials just to heat the infrastructure. So, and why do we need? And why do we need actually the carbon nanostructure? Because it diffuses the heat much more easily and in a faster way. So, to my understanding, this is the first time that is being applied. I'm not an expert on this, but people also from Alexandros are here. I don't want to stick on the carbon-based nanoparticles. It's supposed to be friendly to your understanding, carbon nanotubes or graphene nanoplatelets. In the present study, they have used both cases just to figure out which is the best case. So the first one goes with another patent coming from the same laboratory, is the exploitation of nanobubbles. They can produce water with nanobubbles. There is also one patent, and here you can see this is also a present article with, I think, 500 citations at the moment. So what they are producing from centrifugal pumps, they produce water, tap water, but is enhanced with nanobubbles. And why do we need the nanobubbles? It actually helps to fluctuate the carbon nanostructures. Because if we let them, if in usual water, if you don't use, oh my God, if you don't use this carbon the nanobubbles, then simply the nanostructure will sediment at the bottom of the dispersion. So this is again one advantage. As I say, no mixing ultrasonication stage is needed that we usually do in cement-based materials without this infrastructure. And different cases, different weight percentage, as you can see, it's at a very low scale. Usually, so the preparation comes the nanoparticles. In some cases, we have used a super plasticizer or not. Cement, sand, and standard mixing procedure. There is the strategy goes twofold. the first one was to use small-scale specimens, just a proof of experiment. This is typical 2 by 2 by 8, and they used at outdoor temperature of 3 degrees Celsius. But I think if we can collaborate with Zilliang, we can expose them at even lower temperatures. And of course, we have used AC, and we used temperature measurements with infrared thermometer. And the large experiments were slab specimens. Here you can see, there are the wire connectors to impose electrical current, and here you can see the metallic rods, typical metallic rods for reinforcement, just to heat the cement. And a special device has been constructed. This is the controller dealing with the PID controls of thermocouples and so on. So a lot of electrical measurements. And here I will go to the results. Here you can see the effect of the reinforcement of the GNPs on the small coupons, 2 by 2 by 8. So in here you can see without any reinforcement, this is extremely annoying. Here you can see the time of the experiments over the delta T, the increase of temperature. As you can see, without any reinforcement, the delta T over T is extremely slow. If you use the 0.2 graphene nanoplatelets, here you can see that you can easily increase the temperature at the outer surface. And the results are here without any superplasticizer. Superplasticizers, for those that you are not aware of, is a chemical additive that help the cement-based materials, is a chemical additive, help the workability of cement. So to this end, it is also being dispersed in the cement matrix, and it highly increases to increase the rate of increasing the temperature. And I will pass right now to the slab, the large-scale experiments. Here you can see, again, testing time over temperature, and the starting point was minus 20 degrees Celsius. And as you can see, all different tests increase substantially the temperature, but without, as you can see, without any additives, either superplasticizer or graphene nano reinforcement, didn't show any increase in the temperature. If you disperse the carbon nanotubes or the graphene nanoplatelets at specific levels, these are the 0.2, it was the peak, the maximum for the small scale coupons, then you can see that it's highly increasing over testing time. And here, my apologies again, and here we have put also a threshold of 5 degrees Celsius that is supposed to be sufficient for de-icing. Which one shall we use out of all of this? To my understanding, it should be the first that crosses the 5 degrees Celsius. All the others can also increase efficiently the temperature, but still, at least with this experimental matrix, we figured it out that the GNPs, the graphene nanoplatelets, the 2D materials, are at the moment the most efficient to dissipate heat. Okay, I don't want to stick on the conclusion. I would like to thank also financial support from Greek Republic. And here you can see a very beautiful sea of the city of Kavala with the Byzantine fortress at the peninsula. Thank you very much.